All right, so today we're going to talk about, last class we talked about how to find how binomial probabilities work, what are binomial settings, how do we calculate the chance of any one outcome. So today we're going to talk about like the sum of all the outcomes. What is the average of all the possible outcomes? What is the standard deviation of all the possible outcomes? And so we could do that. You could use the binomial, use the formula to calculate the binomial probability, and we could once again go to our outcomes of blood type, and we could look at what is the chance of having zero. If you have a family with a 0.25 chance of having type O blood, what is the chance that they would have 0, 1, 2, 3, 4, or 5 kids with that blood type? And we would get a distribution that looks kind of like this. And there's the probabilities. So how do we find the mean and the standard deviations? Well, now we're getting back to where we were earlier in the chapter. I got the probability of each one of the 5 possible outcomes. And so we can use the formula we had earlier in the year, which was that the expected value, or the mean of x, is the sum of, that sum came out all messed up, is the sum of x sub I times p sub I. And so we do 0, and then we could also find the variance using the formula of, remember that the variance is the sum of x sub I minus mu sub x times pi. And sorry, my smartboard's freaking out a little bit there in the corner. So, and if we did that, we would get that the mean is 0.125. The variance would be 0.93, and so we take the square root of that to get the standard deviation. Sorry, ignore that. So what we're seeing here, though, is if we do this over and over again with binomials, an interesting pattern comes up. And that pattern is in a binomial setting, and this is on your formula sheet for the AP exam, is that the mean is just n times p. And you're like, well, what does that mean? Well, back here we said the probability was 0.25 of any one kid getting it, and we tested 5 kids, so n times p equals 1.25. And we said that this is, oops, sorry, wrong way. If you look at this as the square root, so the standard deviation, the variance, is just going to be n times p times 1 minus p. So that's n times 0.25 times 0.75. Whoops. And we see that there. If you do that in your calculator, and you will get this number right here, the 9.375. Then you just take the square root of it to get the standard deviation. And so as long as you're in a binomial setting, as long as it's a binomial distribution, the mean and the standard deviation, we don't have to do all the calculations. We just know that it's going to be that shortcut formula. The key here is it has to be a binomial. But if we have a binomial, we can very, very quickly find out what the mean and the standard deviation is without having to do all the calculations. And this is going to play a huge, big time, big important thing as the year goes on. And the reason that's going to be such a big deal is what we're going to see here in a second. So, let's say you're making CDs, and 10% of them have defective copy protection schemes. This is not a big deal anymore, but it used to be, is that 10% of them have a copy protection scheme that could harm computers. A music distributor inspects an SRS of 10 CDs from a shipment of 10,000. Let X equals the number of defective CDs. Now, what is the probability that you will have no defective CDs? Well, what you will see is if you do it as a binomial, you get this answer. But it's not really a binomial because we're not putting those CDs we test back in the stack. And so, remember, the probability that one is defective, and this is the tree diagram, would be there are probability of no defectives. Well, 10% of, so this is going to be 1 minus 0.1 or 0.9. So the first time we look, there's 10,000 CDs, so 9,000 of them are not defective. But if we do it again, there's only 999 CDs, and we got one of the ones that was not defective, and so we keep going, and you'll get this. Now what you will notice is that these two probabilities, while not exactly the same, are very, very close. We don't see a difference until we get to the 4th decimal place. And remember, there's a percent, so like if I told you that one thing had a 35.48% chance of happening and one thing had a 34.87% of chance. I mean, at that point, we'd say they're basically the same. We would agree that those two distributions are basically the same. And this is easy to calculate. This is not. And what we'll find is that in practice, the binomial distribution gives a very good approximation as long as you don't sample more than 10% of the population. And so you'll see this formula here. And n is population size, and little n is sample size. And this is going to become a big deal as the year goes on, because if we can approximate stuff with the binomial distribution, as long as we don't take more than 10% of the population. And here's where it gets really interesting, is that if our sample size is large enough, the binomial distribution becomes approximately normal. And so as n gets larger, and so we have a situation here. This is our probability of remember, P is the probability of success. And remember, the success doesn't mean a positive outcome, it's just how we define the problem. And so as n gets larger, and what we'll see is n gets larger, so n times P here would be 8. And n times 1 minus P would be 2. Here, n times P would be 16, and n times 1 minus P is going to be 4. Here, n times P is going to be 40, and n times 1 minus P is going to be 10. And what you'll see is that this is still a skewed distribution, this one. If we draw the normal curve over it, you can see that it's skewed. Here it's a little bit skewed. You can see this point's a little bit higher. But once we get here, I mean, that's so close to being approximately normal that we can approximate that with the normal distribution. And what we'll find is that we can approximate a binomial distribution with a normal distribution as long as n times P is greater than or equal to 10 and n times 1 minus P is less than or equal to 10. And let's talk about what that means, because I drew them in here. But think about this. This is going to be n times P is the number of successes, where 2 is the number of, quote, failures. And so if the number of successes, the number of failures gets greater than 10, then our distribution becomes approximately normal, and it's very easy to find the mean of that normal distribution, and it's very easy to find the standard deviation of that normal distribution. Which means that all of a sudden, anything that has a binomial setting, we can really quickly figure out what is the chance that it will be above or below a certain point. And this is going to be really the basis. This idea here is going to be the basis for a lot of the stats we do moving forward. This idea that we can use a normal approximation to approximate a binomial distribution, and we can use a binomial to approximate something that's not even a binomial setting, as long as we follow these rules. And this is what we're going to talk about a lot next class. But we need to have these formulas burned into our brain. So go through the video, make sure you understood what I said, and I'll see everybody next class.